Hello friends, this video on Semiconductors Part 3 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till Part 2 before going ahead with Part 3. Now when I talk about energy band, we broadly classify it into two types. I am not saying that energy bands are of two types. Here in this case, as per my requirement, we are going to talk only about two bands. One is a valence band and the other one is a conduction band. So valence band is that energy band which consists of the valence electrons. As I mentioned, when two sodium atoms come closer to each other, let us suppose this is one sodium, this is another sodium. It has got one electron in the outermost shell. This has also got one electron in the outermost shell. When these two atoms will come closer to each other, which electron will get impacted the most? The valence electrons, right? The electrons which are present in the outermost shell. And the least impact would be on the core electron, the electron which is present in the innermost shell. So that means when they will actually start overlapping, some energy levels would be formed. So the energy levels where these valence electrons of, right now I am taking example of two sodium atoms. It will be like hundreds and thousands of sodium atoms will be there. So the energy levels where the valence electrons are residing, that will be known as the valence band. And the band, any band which is above the valence band is known as a conduction band. Because see, in case of sodium, you have your valence electron in this shell. That means any energy level beyond this is all empty, right? Because there is no electron beyond that. So that means any energy level which is beyond the valence band, that is known as the conduction band, right? So when such overlapping takes place, we talk about a valence band and a conduction band. And we generally denote them like this, and this is known as energy band diagram. And on the basis of this energy band diagram, we differentiate between a conductor, a semiconductor and an insulator. This energy band diagram tells us that why semiconductors behave in a different way than conductors and insulators. So here we have this valence band and this is my conduction band. And this is my electron energy. So that means the energy at valence band. Now there are energy levels even below the valence band, because valence band is the outermost shell which consists of the valence electrons. There are inner shells also, but they will have energy even lesser than the valence band. But right now we are not talking about the inner bands, because we assume that the inner bands will always have electrons in them and they are least impacted. So the valence band is the one which will interact with this conduction band. So why this is called valence band? Because it consists of the valence electrons. And why this is called conduction bands? That is interesting, right? Because the electrons, if electrons are present in this conduction band, then that means that those electrons are the free electrons. Why so? Now remember the concept of the metal. I told you how a metal conducts electricity just in the past few slides, right? I told that the valence electron is it is very easy to take out the valence electron. When you apply small amount of energy, that valence electron is pulled out and then it becomes a free electron. So when it was a valence electron, that time it was in the valence band. When it became a free electron, it is in the conduction band. That means when you give a small amount of energy to this electron which is in the valence band, this electron can jump to the conduction band. Now once this electron jumps to the conduction band, it becomes a free electron and it is capable of conducting, right? And this difference between the valence band and conduction band is known as the energy gap. So basically this energy gap is the key component which decides or which classifies a substance as conductor, semiconductor and an insulator. So I hope I was able to explain you what is energy band, right? What is energy band, what is a valence band, what is a conduction band and what is energy gap. So these are the three important things. And on the basis of this energy band diagram, we will now continue with this lesson. Now let us first of all take the example of three different categories of element, right? Let us take the example of sodium, which is a metal and hence a conductor. Let us consider a silicon, which is a semiconductor. Why it is a semiconductor, I'll tell you in the next slide. But for now, I know that, okay, silicon is a semiconductor. And let us take an example of a chlorine. Now, these are three different categories with three different electronic configuration, and we will see what happens when we consider that many atoms of the same kind come together. I mean, how does the energy band diagram vary with each of these cases? So I will discuss first sodium, then silicon, and then chlorine. And now we are not going to talk about a single atom. We are going to talk about an object. Now, I will not talk about any random object. We will talk about a crystal. Now, you must be surprised that why should I talk about a crystal? I can talk about any object because everything consists of electrons. We are talking about a crystal because crystal is an object which has got periodic arrangement of atoms. That means the atoms are arranged periodically. So the distance between each of the atoms is in a particular specific pattern. So that is why we will talk about crystals in this case. So let us talk about the conductors, and we will see how does the energy band diagram of a conductor look like. Now when I talk about sodium, what is the electronic configuration of sodium? Sodium has got an atomic number of 11. So if we write down its electronic configuration, it is 1s2, 2s2, 2p, 3s1. So this is the electronic configuration of sodium. So that means in the first shell, this is my first shell. In the first shell, how many electrons do I have? I have 2 electrons. So this is my 1 electron. This is my another electron. What about the second shell? In second shell, I have this 2 and this 2. So this denotes second shell. So this is my second shell. So how many electrons in second shell? 2 plus 6, that is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So in the second shell, I have 8 electrons. What about the third shell? In the third shell, I have just 1 electron, and this is my valence electron. So if you look at the sodium atom, it has got only 1 valence electron in the outermost shell. So a very small amount of energy is required for this electron to become a free electron, right? Now what happens when a large number of sodium atoms come together? Because right now we are talking about a crystal lattice which will consist of so many sodium atoms. Right? Now let us suppose if so many sodium atoms come near each other, what will happen? Their outer shells will start overlapping with each other. If you look at the figure, you can see that. Now as a result of that, what will happen? The electrons will start repelling each other. There will be a repulsion, and because of this repulsion, a small amount of energy will be generated, which will be enough to bring this electron out and make it free. So that means we are not required to supply any external energy to it. When a large number of sodium atoms are coming closer to each other, the repulsion amongst themselves is sufficient enough to bring out the valence electron and make it free. And once you have free electrons, it will start conducting. So as a result, sodium is a conductor. So this is the scenario in case of all conductors. For conductors, you really don't need to supply some external energy to push an electron from valence band to conduction band. So that means when all these sodium interact with each other, because of their interaction, huge number of energy levels will be created, right? Because every atom will interact with every other atom. So when you look at the valence band will consist of all the valence electrons, right? So now the valence electrons will easily become free electron. In this case, we are able to see that, right? So no external energy is needed to be supplied. That means in this case, the energy gap is approximately 0. There is no energy gap between the valence band and the conduction band, because you really don't need to supply some huge external energy to push the electron from valence band to conduction band. As a result, in case of conductors or in case of metals, you have overlapping conduction band and valence band. So if you look at it, this EV, it always denotes the highest value of the valence band. That means, let us suppose this is my valence band. If this is my valence band, it consists of very closely spaced energy levels like this. Correct? So the energy of this energy level is greater than the energy of this energy level. So EV, which we generally denote everywhere, is nothing but the maximum energy of the valence band. Similarly, when I talk about the conduction band, EC denotes the lowest energy in the conduction band. And this difference between EV and EC is known as the energy gap. But in case of metals, this energy gap is 0. The conduction band and valence band are overlapping because the electrons do not need, the valence electrons do not need any external energy to be supplied to them to become free electron. And as a result, these conductors always have free electrons and they conduct electricity. Now let us talk about semiconductors. In semiconductors, what do we see? We see that there is an energy gap between the conduction band and valence band, but that energy gap is quite small. It is less than 3 electron volts. So that means if we supply some small amount of external energy, then the electron can jump from valence band to conduction band. And as soon as you have electrons in the conduction band, that substance becomes a conductor of electricity. So let us look at the silicon atom. In case of silicon, we have 4 electrons in the outermost shell. So what happens when we bring too many sodium atoms close to each other? Since there are 4 electrons in the outermost shell, it is not very easy to bring out all the 4 electrons, right? Because those 4 electrons are, if it had been only 1 electron or 2 electrons, it is easy to bring them out, because even that atom will also want to get rid of those electrons so that it can become stable. But in such scenarios, it is not very easy to bring that electron out. So that means if we supply some amount of external energy, right, then it can happen that we can bring these valence electrons out of the valence band. So this small amount of energy which is required for the electron to jump from the valence band to conduction band, this energy is very small in case of semiconductors. So it has been found that the energy gap in case of semiconductors is less than 3 electron volts. So these kind of energy band diagram exists for elements like silicon and germanium. And because of this property, or because of this unique property, silicon and germanium are known as semiconductors, because it is not that they are insulators, because if you supply them a very little amount of energy, they can become conductors, right? Whereas on the other hand, if you look at a chlorine atom, how many electrons does it have in the outermost shell? It has 1, 2, 3, 4, 5, 6, 7 electrons in the outermost shell. So it is even more difficult in case of a chlorine atom to bring out these electrons from the outermost shell, because a huge amount of energy is required to bring them out of it. Whereas if you think about the tendency of the chlorine atom, if it wants to get stable, it can just absorb, or it can take 1 electron from somebody and it can become stable. So why should it lose all the 7 electrons? So the chlorine atom is also not much interested to lose all the 7 electrons. Therefore, in this case, if you draw the energy band diagram, you see that the gap between the valence band and the conduction band is huge. Here the energy gap is greater than 3 electron volts. So all such substances which has an energy gap lesser than 3 electron volts behave as semiconductors, because it is possible to supply some external energy of that range and make them conduct electricity. So in this lesson we will see that how do we make use of semiconductors, how do we make use of the conducting property of semiconductors. So now let us have a quick look at the distinction on the basis of energy band concept. Now see, this energy band concept was important. I mean, I discussed so many things about energy levels and all to make and explain you the concept of energy band. That's because it is with the help of this energy gap that we come to distinguish between a metal, a semiconductor and an insulator. If you look at metals here, the the valence band and the conduction band, they overlap. See here, this is EC. So that means this is your conduction band, right? And this is your valence band. So both are overlapping. So you really don't need any energy to supply to make an electron free. In case of semiconductors, the gap between the conduction and valence bands is very less. So if you apply a small amount of energy, you can turn a semiconductor into a conductor. Whereas in case of insulator, the gap is so high that the electrons never reach the conduction band and they are always insulators. So now you understood why these objects are known as semiconductors, because they are not always conductors of electricity, but if you supply them little amount of energy or if they get some amount of energy from somewhere, then they can become conductors. So that is why they are known as semiconductors. So far we understood what are semiconductors. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.